This is a podcast showing some animations on periodic trends. And because our atoms and molecules and electrons and protons are so small, the animations are really valuable in helping you visualize these things. So remember we talked about effective nuclear charge, ENC or ZF, which we called as the force that the outermost electrons experience from the nuclear proton. So let's say that this is an atom with 3 protons and 3 electrons. So there are 2 electrons in the first energy level and 1 electron in the second energy level. Let me just circle it to distinguish them. And this is the force of attraction that the protons exert on the outermost or the valence electrons. The more this force of attraction due to Coulomb's law, the smaller will be the size, because this force of attraction will tend to pull in the electron cloud, making the atom smaller. Now let's look through this interactive how effective nuclear charge changes across the period. Lithium has 3 protons, 3 electrons, and its effective nuclear charge, if you subtract the 2, the total electron minus shielding electrons, you have this much. Now let's look for beryllium. As you notice, across the period, effective nuclear charge increases. And because effective nuclear charge is increasing, the size of atom is decreasing across the period. And let's reset it and look down a group what's happening. Lithium has a certain effective nuclear charge. Let me get rid of this line here. And let's look at sodium. And as you see down a group, because effective nuclear charge decreases, then as the number of shielding electrons are increasing and as the energy levels are increasing, down a group, effective nuclear charge is decreasing, making the size of atom larger. This other one is showing you the atomic and ionic radius. And atomic radius, oh, that was goofy. Atomic radius refers to the size of an atom, while ionic radius refers to size of cation or anion. And if you look at atomic radius, it decreases across a period and increases down a group. And if we look at ionic radius radii follow the same trend. So if you see across a period, down a group, ionic radius is increasing. That's because the number of energy level is increasing down a group, so ionic radius is increasing as well. And you'll experience the same trend going down for the anions as well. But if you look at the, let me just erase this. If you look at across a period, what is happening from sodium to magnesium to aluminum, what happens, all the elements still about group 14 tend to be metals, so tend to lose electrons and form cations, so that the size of cationic radius decreases across a period as the number of protons is increasing and shielding electrons are not really increasing. The effect you notice on ionic radius is the same as atomic radius. It decreases from left to right across a period. However, because the cations have a smaller radius than anion, you see a steady decrease from sodium to aluminum, and then phosphide, because it's its anionic radius, is larger than aluminum, and then you see a decrease in the anionic radius as well. So across the period, cationic radius decreases, and then anionic radius is larger, and then it decreases again. And the reason, if this is an atom A and it is the size of an atom A, its cation will be smaller than atom A, and the anion of A minus, will be larger than A. And the reason for a smaller cationic size is effective nuclear charge is larger. You have same number of protons, but lesser electrons. So greater effective nuclear charge. Also, electron-electron repulsion in the cloud is lesser. When you look at the anion, due to increased number of electrons, there is a larger electron repulsion in the electron cloud. Hence, an anion of an atom will be larger than the atom itself. The next one that we want to see here is, let me erase the ink here, is, let's reset it. Let's say an atom has 6 protons, 7, and has 7 electrons. Which atom is that? You're right, that's nitrogen atom, right? How many valence electrons does it have? So you see in its valence shell, you have 1, 2, 3, 4, 5, and there are 2 inner electrons. Now let's increase one more. The valence electrons increase by 1, but the shielding electrons are still the same. If we increase it by 1 again, now what happens? It's still there. We increase it by 2. Now you see this last electron, valence electron, is in the 3rd energy level. And when that happened, now the shielding electrons have increased, because earlier the electrons in the 2nd energy level were valence, and now the 3rd energy level is the valence shell. So the electrons in the first 2 energy level become shielding. So as you are going across the group, because electrons are being added to the same energy level, you are not adding shielding electrons. But because nuclear charge is increasing, hence there is more effective nuclear charge. But going down the group, imagine you're adding an energy level with each group that you go down. With that, you're increasing just the number of energy levels, so the size of electron cloud is increasing. You're also increasing shielding electrons, but you're increasing the protons in the same ratio, so they kind of cancel each other out. So going down a group, atomic size is larger due to increased energy levels. Now let's look at the electron affinity. And in my previous podcast, I didn't talk much about electron affinity. Electron affinity is when an atom in gaseous state accepts an electron and forms an anion. Whatever is the amount of energy released, or you have to sometimes force it, so absorbed, that is called its electron affinity. And you can see here the anion is larger in size as compared to the atom, because when you add an electron, the size of electron cloud increases due to electron-electron repulsion. Now, few things about electron affinity. First of all, the larger negative value of electron affinity means larger electron affinity. So if an atom has electron affinity of negative 200 kilojoules as compared to negative 100 kilojoule of atom, let's say this is atom A, this is atom B. We'll say atom A has larger electron affinity as compared to atom B. So remember guys, in chemistry, there are no negative numbers. The negative sign means that energy is released. So negative 200 means that an atom, upon accepting an electron, is releasing 200 kilojoules of energy versus 100 kilojoules. And because 200 is greater, the electron affinity of atom A is larger than atom B. So as you go across a period, because the atomic size is decreasing, with the smaller size, as the electron is approaching the atom, there's a greater Coulombic attraction between the protons and the incoming electron. Hence, electron affinity increases across a period. Going down a group, because the size is increasing, electron affinity decreases and the Coulombic attraction decreases. Thank you for listening.